Thank you. Firstly, I would like to thank the organizers for inviting me and putting together a great program. So this work is done with a very talented postdoc, Yuqin Xu, who did his PhD here with Shenke Xu. And the work is on fault-tolerant protocols. So let me just set the stage by making a few lines about error correction. So the idea of error correction is to find a subspace of the Hilbert space of, let's say, n physical qubits to store your quantum information, such that the noise acting on the system finds it like hard to corrupt your information. And one idea for the subspace is take a 2 to the power k dimensional eigenspace plus one eigenspace of Pauli operators called stabilizers. And you choose this subspace in such a way such that in order to go between the states of the subspace, you might need at least a weight d Pauli operator. And these are called the Pauli stabilizer code. And the goal of error correction is to stay within this subspace without destroying the logical information. Although you don't need to be strictly in that subspace, the subspaces can deterministically evolve if you know about the evolution. So that can also work. I will be focusing on quantum LDPC codes for which there exists a basis of these stabilizers such that they're constant weight and each qubit is involved in a constant number of those stabilizer generators. And the main focus of my talk would be fault-tolerant syndrome extraction protocols for these LDPC codes, which is something you can imagine as a space-time dynamics that prepares the logical state in this subspace of the Hilbert space, and then it tries to preserve the logical information through measurement, record, and decoding. And the kind of measurements we do can vary depending on the exact syndrome extraction protocol we choose. So this is a picture of how we usually think of static stabilizer codes, where we perform measurements of these stabilizers and we are in the eigenstate of the stabilizers at one point of time. And then you imagine that you measure the stabilizers again, and then you are in the eigenstate of the same stabilizers over and over as you repeat these measurements. A generalization of this is something on the left side, which is a dynamical code where you also want to be in an eigenstate of some stabilizers, but there can be intermediate states where you are in the eigenstate of slightly different stabilizers. But after one period, you're back to the eigenstate of the stabilizers that you care about. So when I say IST, I mean the instantaneous stabilizer group that you have, and these can vary across some period. And so that's what I mean by a dynamical code in general can have a time-varying instantaneous stabilizer group. And even the logical space, even the logical space can evolve in some deterministic way, and it can be generated also through these measurements. Meaning that you might be starting with some sort of, you might be starting with some qubits, and you may not know whether you are whether you have a logical qubit or not. But as you measure, you are in some topological, let's say, toric code stabilizer eigenstate, and so you have some qubit, and that qubit can dynamically evolve over time. So this is a general idea where you can have a dynamically generated and evolving logical space, and somewhere in between lies a subsystem code where you also have these time-varying instantaneous stabilizer groups, but we usually think of a static logical space. And the theme of my talk is to say that the fault-tolerant syndrome extraction protocols can be generally understood within this dynamical framework. And I also kind of lied when I said that on this side, on the static side, we have the stabilizers remaining static. because as it was shown in Alexis Morvan's talk, like these stabilizers evolve under the unitary gates that you're doing for your measurement circuit. So in that sense, these two pictures are basically, they have the same flavor in the sense you have instantaneous stabilizer groups. Okay, so here I'm showing the 422 code, and there are various ways to extract the syndrome of these stabilizers, right? You can measure these stabilizers in various ways. You can do the single ancilla syndrome extraction circuit, or you can do this cat state-based syndrome extraction, or this Canil gadget. And all of these processes can be useful depending on the kind of fault tolerance you want for a certain noise model. For example, this Shor's approach, which uses a cat state as the ancilla, this kind of distributes the measurement process and it reduces correlated errors at the cost of these extra resources. So here we are seeing that we have various examples of syndrome extraction. And at the circuit level, all of these circuits look quite different, right? One uses just a single ancilla, the another kind of fans out into a cat state, and the last one brings in a full encoded block. But there is this language of ZX calculus and ZX equivalences in that calculus, where all of these circuits become equivalent to this ZX diagram. So that means if you translate each of these circuits into ZX calculus and apply the standard ZX rewrite rules, you can collapse them down to this kind of diagram. So ZX calculus is a very useful language where we can sort of understand which syndrome extraction protocols are inherently different or even their fault tolerant properties. So let me just give you a quick idea of ZX calculus. So ZX calculus, as I said, is a graphical language, and it's a graphical language for linear maps between qubits. And these linear maps can be expressed as using diagrams called ZX diagrams. And ZX diagrams has these generators called X nodes and Z nodes. And this is the definition. So if I have a node with this face, it looks like this projector. So you can express different circuits in terms of these kind of nodes connected together, contracted together, so it's a kind of a tensor network. One important property of these ZX diagrams is that you can topologically deform them, and it doesn't affect the linear map that it represents. And this is what I would use when I'm constructing a fault-tolerant protocol. So here I'm showing just the two generators of ZX diagrams. So so there are these ZX rewrite rules that let you go between different ZX diagrams. So what does a simple line mean? That's just identity. And you can put a Z node over here. And so that just keeps it the same because this is the definition of the Z node. And then you can keep adding more Z nodes. And similarly, you can have a line with these X nodes, and you can have these together. And if you have just a single node with a line coming out, that means it's a state. So this is the plus state if you have a Z node with a single line coming out. And yeah, you can keep applying these sort of rules, and you can try to go between different diagrams. Here I'm showing the simplest ZX rewrite rules. And so let's try to see how these rules help us with the C0 gate. First of all, with the Z and X nodes that I showed you before, I can express the C0 gate like this. This is how you can, if you really write those projectors and do the contraction along this leg, you will get the C0 gate. And this C0 gate, we can apply some rules and express the C0 gate using this diagram. So these two diagrams are equivalent when these measurement outcomes, so here when I say that these two nodes are joined together with this node M2, labeled by M2, that means I'm measuring an operator over here. And that measurement yields this eigenvalue M2. And this is M1, meaning that you're preparing a state with eigenvalue M1. So when all of these things are +1, you get an action which is equivalent to C0. And what I have done here is I applied ZX rewrite rules on this diagram and expressed it using pairwise measurements up with some ancilla. So, what you can also try to do over here is take these C0 gates that appear and simply use the pairwise measurement compilation that I showed you and express all of these circuits in terms of pairwise measurements, if you want. But a naive replacement may not yield the most efficient circuit in terms of pairwise measurements. But you can do this if you want. And then after doing that, you can apply ZX rewrite rules to map all of those different compilations into this single ZX diagram. So using the tool of ZX rewrites, there have been advancements in taking measurement circuits and turning them into circuits of low weight measurements while preserving the distance. But note that if you just take the usual syndrome extraction circuit of, let's say, toric code and apply these ZX rewrite rules, which, like in this paper, there's a distance preserving ZX rewrite rule that they apply on some starting syndrome extraction circuit and convert it into pairwise measurement circuit. And here, you try to reduce the weight of the measurements by doing weight reduction algorithm and then compiling the starting circuit in terms of pairwise measurements or smaller weight measurements. So you can do this, but note that if you start with a circuit that has certain properties, like a trivial logical automorphism, meaning that it has trivial action on the logical subspace. So then when you do the ZX rewrite, you will necessarily, when you do these sort of rewrites, you will necessarily get that equivalent circuit with a trivial automorphism. But in the kind of setting that I'm interested in, especially flow K codes, I might be interested in non-trivial logical automorphisms. So the logical state evolves after like one period of your measurements, for example. So we might want a recipe that also outputs these non-trivial automorphism codes. And that's how the flow K codes were written down, like the non-trivial automorphism codes before the ZX age were written down. They had some interesting, some of them had interesting non-trivial logical automorphisms. I write some examples here. And these constructions, though, were guided by the intuition of the topological phase of matter or just writing down certain sequences of measurements by hand. So the natural question is, can we find a general construction principle that unifies these approaches? For example, something like this, and taking intuition from the ZX rewrites, and output codes with non-trivial logical automorphisms as solutions of the dynamics. So using ZX diagrams, we can think of syndrome extraction not as a specific circuit, but as some sort of general template. And this not only recovers the usual stabilizer checks, but it gives us the freedom to specify that the logicals are morphing in a certain way. And once we allow ourselves to sort of deform these diagrams in space-time, we get to this idea of space-time concatenation, which is the principle I will try to emphasize. Here I'm showing that you can go from some sort of diagram to ZX diagram, and you can say that maybe you want to have this kind of automorphism within this diagram at some point. And you can try to massage it in a way that you get the kind of more automorphism you want, but I haven't specified that yet. So let me just say how I'm going to do it. So on the left, I have this box, which I call a gadget M, with the time flowing upward. And at the bottom, we support a stabilizer group. on these incoming legs. And the action of the gadget M, maps it to a stabilizer group on these outgoing legs. And for the purpose of syndrome extraction, I will say that this outgoing stabilizer group is same as the incoming stabilizer group. And furthermore, we can decompose this global gadget, this sort of gadget M, into local gadgets, which are shown on the right side. And these local gadgets are connected to each other with these legs that I will call as internal legs. And each of these local gadget is a Clifford encoder. It maps the incoming and outgoing poly operators sitting on these legs onto poly operators sitting on these internal legs. So so that's how the construction will work. And you might, if you know about quantum Lego codes, this way of connecting gadgets together might be a reminiscence of how the Legos are connected for building static stabilizer codes. Okay, so now how do we actually realize these gadgets as circuits? I just said that there is some input stabilizer code, there's some output stabilizer code, and it's the same as the input stabilizer code because we are doing syndrome extraction. But how would you realize it as a circuit? So the point is that once I specify these input-output relations on these gadgets, then I can write a ZX diagram for it. There's a recipe that I will use to write a ZX diagram. And once I write a ZX diagram, I will express that ZX diagram in this form where I have some sort of spatial concatenation, which I call as spatial encoder, meaning I concatenate the physical qubits with some small code. And then I do measurements across the gadgets, meaning that this MI gadget is connected to some gadget above it, and I do measurements in between those gadgets. And then I do this dual spatial encoder, which sort of unconcatenates the qubits. So in an actual circuit, this dual spatial encoder will sort of merge with the spatial encoder and give you some sort of action on the physical qubits. We don't actually do this in like the circuit. It's the measurements that doing this part. But in the diagrammatic sense, it looks like you're bringing some legs together, sort of bring into one leg of the ZX diagram and then opening it up again. And so you bring it into this form, and then that ZX diagram, you can actually just say that these are the physical legs, and this is how the actual physical circuit looks like. Okay, so let me describe all of this using an example of the toric code. So the Floquet toric code by Hastings and Ha is as follows. You have this, you can define it on various lattices. They defined it on the honeycomb lattice in the beginning, and in subsequent papers there is this version as well where this is another trivalent lattice. It's called the 844 lattice. And here you can, you have these three colors of edges, and you can define a XX measurement on the red edge and the YY measurement on the green edge and the ZZ measurement on the blue edges, and you can just do like red measurements, then green, then blue, red, green, blue, and so on. So that's your measurement sequence. And that basically gives you instantaneous states that look like effective toric codes once you reach the steady state of the dynamics. So this is how the instantaneous stabilizer group looks like in the round in which you measured the R edges. So this is how it looks like, and this is a toric code, and there are these effective qubits sitting on these squares. So it's as if you concatenated the physical qubit with a 4-qubit code, and these are the effective stabilizers. And this is your small code with which you have concatenated. Right, so that's the instantaneous stabilizer group in the R round. And similarly, you have instantaneous stabilizer groups in the green round and the blue round. And this is how the effective qubits look like in those instantaneous steps. So here you have this kind of toric code. Here you have another kind of toric code. Yeah. So we want to see, you have this sort of instantaneous state, and after you do one cycle of the measurement sequence, like RGB, you get automorphism, meaning you apply a certain transformation on your logical space, like how the Marth and the swap. So how will we construct this code in our approach? That's the question. And what I want to do is, I want to feed my approach, this ISG, in the R round. And this is the effective ISG, meaning that I'm looking at the effective qubits of the toric code. And then I say that this is the input and this is the output, and I want the protocol, I want the scheme to give me a protocol that looks something like this. And so that's the gadget. The gadget takes in this effective toric code and it outputs the effective toric code. So how will I find this gadget? That's the question. So on the left here, I have the gadget picture for the toric code. So for every qubit, I write a gadget. And there are these incoming legs and outgoing legs and these internal legs. And there are polys sitting on these incoming legs, which are the polys of your incoming stabilizer code. And the condition that we want to impose on these gadgets, one condition is that they should map the stabilizers to identity when you, they should map the stabilizers, the poly operators associated with the stabilizers. When you map them onto the internal legs, you should get identity. So that's one condition, because in the ZX diagram, you want to measure them. You want to collapse them to some eigenvalue, so C times I. So that's the constraint we have. And the other constraint we want on this map of this sort of gadget, notice that I'm just taking one gadget over here. Other constraint is that the incoming algebra of the poly operators should be preserved when you map them onto the internal legs. And so here, let me actually go to the next slide. So here I'm showing what are the constraints due to the preservation of the incoming poly algebra, and maybe also the outgoing poly algebra, because we want to map both of them to these internal legs, the incoming and the outgoing. And so here I'm showing how the incoming poly operators map onto these bond legs, these internal legs. And I've chosen a certain kind of mapping which maintains this algebra based on the anti-commutation of the poly operators, the incoming poly operators, and also the constraint that the stabilizer should map to identity. So based on that, I chose such a thing, and I got this solution. So that's how it should, how these gadgets should map each incoming poly. And once you write the map of each incoming poly, you can write a poly stabilizer tableau. So here, this is the incoming leg, here this is the outgoing leg, and I have four legs in the plane of the gadget, which are the internal legs. And this is how the X maps onto certain polys. I just need to choose P not equal to Q to satisfy the constraints I mentioned. And once you write this tableau, first thing you want to check is what is the rank. So I had 6 legs, and here I have 6 independent entries, row entries in this tableau. So the specification of the gadget is complete. And once you have a complete specification, you can disentangle each row into one qubit operator, and doing that process iteratively gives you a certain ZX diagram like this. And if you have the ZX diagram, we are going to invoke the deformability of the ZX diagram, and I'm going to turn the ZX diagram into this kind of diagrams. Out is missing over here. So I get this thing, and over here I have another kind of node, which is called the Y node, and it's related to the X node with these sort of Z nodes. So now I got a ZX diagram for one gadget, and I'm going to join these gadgets over time because I'm repeating this sort of cycle, and I can join it in this form, and I can apply a ZX rule which changes this sort of sub-diagram into something like this. And this looks like ZZ measurement, and here this will join with neighboring gadgets to give you X and Y measurements. So how would you join them? basically, this is the gadget I got, and these are the solutions of the other gadgets, and I will join them like this on the square lattice. And so I end up recovering the Floquet toric code using this gadget picture. And you can also look at the automorphism in this gadget picture. If you take the map of this long logical operator, it goes to the other side. So it does the automorphism that the Hastings-Floquet code does. And in that sense, because it does this automorphism, this code is inequivalent to the single ancilla syndrome extraction circuit, because there you don't have any automorphism. So you need to take 2 copies, 2 rounds of this thing, to actually then map it to the single ancilla syndrome extraction circuit. So how did we recover this solution? It's also dependent on how many legs you choose to join between the gadgets. This was the simplest solution we found. If you have more legs between the gadgets, you can find other solutions. In fact, you can find this single ancilla syndrome extraction circuit, which is actually equivalent to something called the CSS Floquet toric code. So just by changing the number of legs between those gadgets, the internal legs, you can recover more and more solutions. So you might want to start with the minimum number of legs, and we have a way to specify what is the minimal gadget decomposition you need to find the solution with the constraints that I mentioned. And in this case, it yields this particular code. In general, you might want to, again, like for any stabilizer code, start with this minimal gadget decomposition, look for a solution, and go from there. So in general, as I said, we could have had any stabilizer code in this sort of prescription and look for these fault-tolerant syndrome extraction protocols. So we looked at this bivariate bicycle code. So this is how it looks like, and so the gadget decomposition also has to look based on the Tanner graph of the stabilizer code that you're feeding in. Because there is an algorithm that we have that if you have a pair of qubits participating in an X and Z stabilizer together, then we add an edge between their corresponding gadgets. And so that's how we write this sort of gadget decomposition. Here we have like 2 legs because we wanted to find a solution. We couldn't find it with 1 leg, so we added 2 legs. And there may be some connection between the Tanner graph and how many minimal number of legs that you need. We haven't worked that out. And so for the Floquet version of this BB code, we recover this sort of ZX diagram, which tells you what sort of pairwise measurements you need to do. Okay, and also we have some automorphisms in some of these new Floquet codes we have written down using this sort of recipe. So to guarantee, so I showed you how this construction outputs new examples, but we need to guarantee fault tolerance. And one condition we impose to have fault tolerance is called this macroscopic logical map condition. In the current version of the paper, we call it something else, but this is a new name that I used for the talk. So the idea of this condition is that the logical operators should never map onto short operators when you apply this mapping of the gadgets onto the internal legs. So if you see the map of the logical operators, they should never map onto short operators. If they map onto identity, meaning you measured them. So we don't want them to map to identity for sure. We also don't want to map them to short operators. Because if they did that, that would correspond to a constant weight undetectable logical error in spacetime. So formally, this condition says that for any logical operator W, its image under the gadget map should not be short. And this also implies a sanity check, which is that the dimension of the incoming and outgoing poly operators onto dimension of the maps of the incoming and outgoing poly operators onto these internal legs. If those maps have our identity, right? So there's a subset of operators which map onto identity. We are saying the dimension of those operators should be 2n minus k, because we have some number of stabilizers from this side, some stabilizers from this side, and k logical qubits. These are the incoming and the outgoing codes. This is a sanity check which we might want to do after imposing this condition. Okay, so for showing that this condition works, we assume that any undetectable space-time error can be propagated to just the internal legs without blowing up in size. Let me say what that means. I have this gadget map which says incoming poly operators or outgoing poly operators map onto the internal legs. But using this map, I write a space-time dynamics. I write a circuit, right? So the circuit is kind of a fleshed out version of this map, and there is a flow of poly operators through the circuit, right? So the point that I'm trying to make is that if you have some undetectable space-time error in that circuit, we first want to move that error to the internal legs, the part of the space-time dynamics which corresponds to the internal legs. And once you move that to the internal legs, we assume that then you can move those poly operators to, let's say, the outgoing stabilizer code. So if there is something undetectable and you move it all the way to the outgoing code, that means it has to be either a stabilizer or logical if you are able to propagate it, right? So if it was short, and if you map it all the way to the logical operators on the outgoing code, meaning that there is a logical operator in this outgoing code which maps onto a short operator on the internal legs. And those are the cases which we have explicitly avoided. Right? So those are the cases that are avoided by construction. We just never considered those solutions. So if you can propagate such an undetectable operator to the outgoing legs, then all we need is the macroscopic logical map condition, which says that no map of the logical operators on the outgoing legs, when you map it onto the internal legs, no such map is short-weighted, right? So that's one thing. And this is something we had assumed in the paper, and after discussions with Jongwon, I realized that we have not proven this underlying assumption of propagation, but given Jongwon's proof about the propagation of undetectable poly errors all the way into the future earlier this week, I believe we could also prove it in this setting using some sort of connectedness of the ZX graph for the Clifford encoders that we construct. Or we could cite as a result if it applies to our case. So that's the condition we have. And then the second condition is more constrained, which is called the strict k-locality preserving condition. So the first condition is to maintain macroscopic code distance. The second condition is to not have the code distance even change by a factor of c, by some constant factor. And so here, as you saw that the gadgets in my construction for the toric code, they were mapping the poly operators onto these nearest, onto the legs connecting to the nearest gadgets. In principle, you could have such legs connecting to faraway gadgets, and then you can consider maps onto those legs connecting to faraway gadgets, but we don't allow that kind of possibility. And so that's what we call a strict locality preservation condition. And this sort of condition intends to make your construction not suffer from something like hook errors that can reduce the distance by a constant factor. Okay, so that's the way we try to guarantee that the space-time code distance is greater than the code distance of the static code for which we are considering this syndrome extraction protocol. So I have 5 minutes? Yes, so let me just say that this sort of construction is very general in the sense that it's kind of hardware first, because let's say you have a missing qubit or a missing connector in your hardware. What I can do is, in my gadget decomposition, I can say that these two gadgets are not connected with some leg, because that connector is missing in the hardware. I could also remove the gadget if some qubit is missing and impose input and output stabilizer constraints and still look for compilation of syndrome extraction. So here, this is the toric code. This is the gadget solution for one of the white gadgets that I had. And now one of the connectors over here is broken. So if it's broken, I can look for, I can sort of map the poly operators in a different way such that all my constraints are satisfied, which is mapping the stabilizers to identity and making sure the poly algebra is preserved. And so I find a different solution over here. And this is a 6-round schedule, which sort of works when you have, some sort of fabrication defect, in this case, the broken connector. And this broken connector analogy can be generalized to a boundary, because I can break all of these connectors in this Floquet toric code that I was showing you. I can break all of these connectors, and that gives me the boundary. And then I can try to look for a schedule, and I find a boundary schedule for a planar Floquet toric code. Right? If I actually apply the 3-round schedule on this sort of boundary toric code, then the macroscopic logical map condition will not be satisfied because the logicals will map to identity. So we can check that using just the gadget picture, because this 3-round schedule ends up measuring the logical at the boundary. And in Jungwon's talk, he already showed you Christoph View's example, where instead of mapping the logical to identity, which corresponds to measuring the logical, there the map of the logical onto the internal legs is constant weight. And so we also eliminate that solution when we are looking for planar solutions, because we don't allow such solutions. In fact, what we end up finding always is some sort of rewinding solution when we look for these boundary or defect kind of solutions. So to summarize, this sort of approach of space-time concatenation to generate fault-tolerant protocols, I feel it's a hardware-first approach for compiling dynamical solutions of syndrome extraction. It includes non-trivial automorphism codes. And currently we are applying this framework because it's based on this sort of deformable ZX language, ZX calculus, ZX diagrams. We are applying this framework to non-abelian Floquet codes and fermionic Floquet codes. With that, I would like to thank you for the attention.
Okay, questions?
Yeah, thank you for your talk. I really like your formalism. So for this k-local part, when you have automorphisms, do they correspond to k-local finite depth unitaries?
K-local part where?
Like, so no, when you use it for, like, say, bivariate bicycle codes. So for
bicycle codes. Yeah, so we have a pairwise measurement that connects faraway qubits.
So basically you can do QLDPC setting, right?
Yeah.
So if you have an automorphism, do you have a statement that that's related to a k-local finite depth unitary circuit for that automorphism?
Yeah.
Okay. And are you able to use it to find new gates in these codes?
We haven't investigated the gates as much. For this particular construction, we mentioned the automorphisms, or like whatever construction we have in the paper, we mention what we get. But there needs to be more investigation into the automorphisms for those LDPC codes.
Okay, thank you. But have you found automorphisms specifically, say, for bivariate bicycle?
I think, yes, for one, we have multiple solutions for the BB codes, and yes, I think for one of them, we have an automorphism.
Have you compared them with the gates that are known for that code?
I haven't.
Haven't yet. Okay, good. But this is great that you haven't.
Yeah, we mostly worked that example out, and there needs to be more investigation.
Yeah, thank you.
Questions?
Okay, I can ask more questions.
Yeah, question.
Yeah, just a small question. Yeah, on the BB code like gadget that you had, there were like 5 long-range legs.
Mm-hmm.
Where does the 5th one come? I guess I can understand from like the Tanner graph, the 4 out of the 5, but where does the 5th one come from?
Let's see. So I have 6 in total. I have 6 in total because there are 4 of these and then 2 over here.
Okay, but they're connected to the same?
Yeah, so sometimes you can have like 2 legs between the gadgets. Yeah, and this kind of relies on how we try to map the stabilizers to identity and make sure the polyalgebra is preserved. Yeah.
Okay, so but it's not exactly like the Tanner code connectivity then?
There is some connection to the Tanner code connectivity. The way we look at the Tanner graph is we check how many, if there is a pair of qubits involved in an X and Z stabilizer, then we try to add the edge. And sometimes that's the minimal gadget layout, but sometimes you might want to add more edges if you didn't find a solution. I don't know for sure. I think there should be some result on this which says that for a minimal gadget, or what is the minimal gadget for which you start finding solutions. Yeah.
Thanks.
Can I ask another question?
Yeah.
So for K-local setting, what can you currently say about fault tolerance?
It doesn't change. It's the same result, like this macroscopic logical map condition. This is something we apply in general. Like, it's not for just local codes.
I see, thank you.
Yeah.
Any final questions? This one.
Yeah, so you said like you can kind of handle a case when there's some defect, like some missing link or some missing qubit.
Yeah.
So do you know like what does the solution look like in that case?
Yeah, we have worked that out in the paper. So you need to define how the input stabilizer changed. So that's not something automatic. You need to tell us like how the input stabilizers have changed on this new graph.
I see.
And then it's just a new code and new gadgets.
So for example, like, are the new measurements that you need to do like still a 2-body or like?
Yeah, that you can take care of. Yeah, you can keep them 2-body. It's just that the input stabilizers, you might need to tell that, okay, this is the stabilizer group. It could be automated perhaps because, there's a well-defined way. When you lose a qubit, you could say this is a new set of stabilizers that you're inputting. But for us, like, you tell us the stabilizer group and then we feed it to this gadget. And then it will do its thing and try it out.
Okay, thanks.
Okay, let's thank Arpit.